take pointer.
Okay.
Very good, it is looking.
Okay.
We will start, sir, then. Now it
Yes,
is
okay.
visible. Huh?
Okay.
Yes, sir. A very good morning, Honorable Professor Kailasnath, sir, from International School of Photonics, from where we have taken idea to start the program MSc Photonics. They have taught us a lot of things at International School of Photonics. There were Professor Nampuri, sir. He has given a lot of guidance in designing the curriculum, setting up the laboratory at the initial phase of our college when we started the MSc Photonics as a course in 2007. So I am very happy and glad to have a resource person from a world's best institute in photonics, International School of Photonics, Cochin University of Science and Technology, Kerala, for this AICTE Training and Learning Academy sponsored 1-week online faculty development program on photonics, active learning in optics and photonics. Professor Kailasnath Madanan, sir. A very good morning to you, sir, and very good morning to all the participants. Now I request one of my participants, Dr. Vidyadevi Patil, ma'am, to introduce Dr. Kailasnath, sir. Dr. Vidyadevi Patil, ma'am, please.
Yes, sir. Good morning to one and all. I, Mrs. Vidyadevi Dilip Patil, is very much thankful to Dr. Abhijit Yadav, sir, HOD and FDP coordinator of Rajarshi Shahu Mahavidyalaya, Latur, for giving me such a wonderful opportunity to introduce today's guest of honor and eminent personality, Dr. Kailasnath Madanan, sir. Welcome, sir. Professor Kailasnath Madanan, sir, is working as a professor in International School of Photonics, Cochin University of Science and Technology, Kerala. Sir has completed his MSc in Physics, M.Tech in Optoelectronics and Laser Technology, and completed PhD in Photonics. Sir has published more than 46 research papers in a reputed journal and international conferences. Sir has developed one of the technology, that is polymer optical fiber fabrication, and that technology transferred to Sterlite Optical Technologies Limited, Aurangabad. He has received research fundings from various institutes, universities, and from various countries. He completed number of projects such as Science Popularization Program Celebration of Year of Light funded by KSCSTE. He also completed project on Erasmus Plus International Student Mobility Program with University of Gothenburg, Sweden, which is funded by European Union. He also completed one of the project, that is development of optical fiber based devices for sensing application, which is funded by
I think Vidyadevi ma'am has lost her connection somewhere. Sir has a huge biodata. When I have gone through his biodata, he's a famous international personality in the field of photonics, optical fiber sensors. Now I request Professor Kailash sir to start his invited talk on the subject polymer fiber optic micro lasers for sensing application. Kailash sir, please sir.
Thank you
Yes,
for the nice introduction. Am I audible?
Yes, sir. Yes, sir. You are perfectly audible. No problem.
Okay. Very good morning to all participants. Myself, as mentioned, Kailasnath from Cochin University of Science and Technology. I'm happy to share some of our findings and works that we do at CUSAT in the field of sensing with you. And basically, this talk will be based on an area which is called micro-sized lasers, which are made of polymers, and how they can be used for various applications of sensing. But I found that my topic that was listed as a fiber optic sensor, as I mentioned earlier with Abhijit.
Yes.
So I would like to
Yes.
just to have a brief introduction about the sensors, fiber optic sensors, then optical sensors in general, and then I will go to my topic. And one more question, Abhijit, you have a photonics program running there, right?
Yes, sir. Yes, sir. MSc Photonics.
Is it a 2-year program or 5-year program?
It is a 2-year program, sir. It is a one of
2-year
those
program. Okay.
Yes. MSc.
Okay.
Yes, sir.
Thank
Yes.
So, with your permission, before going into the details of the topic, let me spend 1 minute about my department. My department was established in the year 1995 in Cochin University of Science and Technology. And we have 2 prestigious programs. One is a 5-year integrated MSc in Photonics, for which students join after their +2, after a common admission test conducted by the university. And we have a 2-year MTech program in optoelectronics and laser technology. And I am proud to say that around 75% of all our graduates, they are employed abroad. We have a 20 number intake for 5-year integrated program, and every year about 14 to 15 students out of these 20 students, they get opportunity to do PhD abroad in various reputed organizations and institutions. And we have many active memorandum of understandings, that is interinstitutional agreements running currently, and many of our students are benefited as exchange students, or they can do their master project over there. And students from these universities, they come to our department as well. And most of my PhD students, they are very much benefited by these interinstitutional agreements. This is a brief idea regarding our faculty members. We are 8 faculty members, and the various disciplines are detailed here. And let me spend few seconds more. We have developed an optics kit, which was as a program like International Year of Light, that was funded by the Kerala government. And during that period, we were able to develop this optics kit, and which is a very useful and very cheap in terms of cost, and which we demonstrated, and which we produced and supplied to around 100 schools in Kerala. And from that year onwards, we are continuing our outreach programs with either the students coming to the department or our faculty members going to the nearby schools. And about 100 very rural village schools in Kerala were gifted with this optics kit, and most of the basic optical experiments at the school level can be conducted very easily using that optics kit. And we were also funded by OSA and SPAE for this purpose. Coming to the optical sensors in general, I understand that you have already had a course on optical sensors from the industry also. Basically, in our day-to-day experience, the kind of sensors that we we encounter or see in our are basically this kind of things like ambient light sensing or optical heartbeat monitoring mechanism, breathe, and these kind of things that we actually see in our day-to-day life. Most of them, they have an emitter, a receiver, and in between the light is actually interacting with some kind of medium. So coming to the fiber optic sensors, we have this broad classification for fiber optic sensors in terms of extrinsic and intrinsic. This is one type of classification that we generally do. In an extrinsic sensor, the light actually come out of the fiber, it interacts with the medium, interacts with the object under study, and then we have to it has to enter the fiber back, and then it is detected. But in the case of intrinsic, the light remains in the fiber in the waveguide while being interacted with the outside medium. It can be displacement, force, pressure, temperature, etc. Concentration, different types of parameters it can be. So the fiber optic sensors, it uses light guided within an optical fiber to detect any external physical, chemical, or biomedical parameter. So these are some of the basic parameters which will determine the signal that is developed by an optical fiber sensor. So one is the power emitted by the source, the coupling efficiency of the input and output fibers with the modulating element, and the transmission efficiency of the fiber, the response of the modulating element, and the responsivity of the detector, etc. These are some of the general ideas. And coming to the optical fiber, I won't be using much mathematics or formula in this talk, but these are 2 or 3 slides that I am going to use in the beginning. So if you are familiar with the waveguiding condition or optical fibers or any planar dielectric waveguide, the condition for the guidance of light in any waveguide is that there should be constructive interference, okay, among the waves. So you have a wave here which is reflected multiple times, and then we can see that if the wavefronts associated with these rays are shown in red and the wavefronts are shown in blue, okay, assuming them as plane waves. So the wavefronts are common for these multiple rays. This ray and this ray, they are separate, but they share the same wavefronts. That means there is chance that they will constructively interfere. So this is true even if we imagine multiple rays which are moving parallel to each other. So they can constructively interfere, but note that every ray that is propagating parallel to each other doesn't result in constructive interference. So whatever rays which are moving parallel and are able to constructively interfere, they will lead to a mode. So that angle of incidence is a permitted angle of incidence, and corresponding to each angle you have a mode that is propagating in the fiber or any other dielectric medium. So what is important to note here is that if you calculate the electric field at any location within the region, and you can see you can select any parallel rays which are moving in a desired direction. They can meet at different locations, and if you consider the electric field pattern throughout the cross section of the waveguide, you will get patterns like this. So for example, for a particular angle you have this m is equal to 0, that is one mode, that is the second mode, the third mode, etc. So this kind of patterns you can imagine for every possible angles that are allowed to interfere constructively. So one important thing to be noticed here is that if you look at the electric field pattern that is formed here, you can see that it has a harmonically varying term something like this, and a second term which has a time dependence. This is a propagation part, and this is doesn't have any time dependence, the first part. So a harmonically varying function along the y direction. Y direction is this direction, and this is the propagation direction. So some field is actually some kind of field patterns are generated by each of the allowed angles, which results in constructive interference. So each of the modes, they form something like a standing wave pattern along the y direction. Still they are moving along the z direction. You can see that some part of the field is actually leaking into the cladding. So in the you can visualize it something like this. So you have a mode, a particular angle, and you have another mode, another angle, you have another mode, another angle. But to be noticed here is that the penetration into the cladding, that means the light actually goes into the tunnels into the forbidden region. So this is the higher refractive index, and this is a low refractive index, but light is supposed to be confined here itself, but it is actually leaking into the cladding. And the extent of this leakage is different for different angles. And this is the ray picture, and if you consider the wave picture, you can see that the extent of penetration is different for different modes. So even though the light is leaking into the forbidden region, this region is you can tap this field, portion of this field which is leaking into the cladding for many sensing applications. You may be familiar with the evanescent waves. So I am just talking about the evanescent waves right here. So like this is the field that is propagating. For example, m is equal to 0 mode. So the fundamental mode, if you imagine, this is the electric field pattern, and this can propagate in the z direction, for example. But some part of the field is in the cladding, some part is in the core. Okay, so here also the same thing is actually written for any pattern, electric field pattern that is propagating. Some part of it is actually leaking into the cladding, and the part that is leaking into the cladding is evanescent wave. It is an exponentially decaying field in a direction perpendicular to the core cladding interface. How much distance that this field can penetrate, so that will depending on this alpha cladding. Okay, so the attenuation of this cladding is given by this expression. All the terms are known, the lambda, n1, n2, and theta I. Theta I is the angle of this incidence. So what we see here is that certain part of the field is actually penetrating into the cladding, and that field can be used for sensing applications. That is actually shown here. So here you have a core and the cladding, and for certain region of the fiber, the cladding region is removed. I mean, the cladding is removed actually. You have core alone, and the evanescent field leaking into the cladding is exposed to the external medium here, and the evanescent wave can interact with the parameters, whatever parameters or chemical or biological or physical parameters here. So that is the basic idea behind any evanescent wave sensor. So this is the basic expression regarding that. We are not going into the details of this kind of sensors, but I'm just mentioning what is the significance of this kind of lasers, sensors. So the evanescent wave fiber optic sensors, for example, here you have a light source, you have a spectrometer or any other detector, and you have certain region of the fiber, you remove the cladding. And in this particular example shown, some kind of coating is given into the core. It can be a gold coating, for example, and over the gold coating, you can immobilize certain antibodies. Antibodies can be immobilized, and these antibodies can bind some antigens so that the local environment and the dielectric constant can be changed, and the absorption properties can be changed so that that change can sense the light that is present here in this cell. So this is the expanded view of this region. So it can have this kind of antibody antigen binding possible. So here again you have a tapered optical fiber. So one method to expose the evanescent wave more into the surrounding region is by tapering of the fiber. So here the fiber is tapered so that the more evanescent field is exposed to the surrounding medium. Okay, and here you can have certain types of coatings, for example, so some kind of sol gel coating, for example, and this sol gel can interact with the surrounding medium and thereby change the dielectric constant or other parameters so that it can be used as a very good sensor. And this is actually summarized here. It can be a tapered region that can be acting as a sensor. Here it is a tapered tip. This is just a tapering. Here the tip is tapered, and here some kind of nano wires can be attached to the tapered region, or some kind of gold coating, or some kind of nanostructures that can be attached with this region, which can act as a sensor. Also, it can be something like a hollow kind of a structure, a capillary, and if it is a capillary, you can use this capillary to hold some analytes or liquids, and you have a tapered fiber in touch with that, so that the evanescent wave can be coupled into this capillary, and it can form a resonating mode that we will see in detail later. Okay, another important class is surface plasmon resonance based sensors if you come to the optical sensors. So this is actually termed as a single technology that has the capacity of photonics and the smallness of electronics. So if we compare the capacity of electronics today, it is highly miniaturized, okay, but the photonics has a capacity to process, a huge amount of data you can process with photonics, but it is bulky. But in electronics, a considerable amount of miniaturization has already taken place, and the amount of data it can handle is very less. So the plasmonics is the field that actually unifies these two advantages. So what is happening here? You have a something like a dielectric. You have a dielectric and a metal layer coated onto this. And the basic experiment that is shown here is the Kretschmann configuration, where you have a prism, and over the prism you have a metal layer that is coated like gold or silver that is coated, and the light is being sent from one side and it is getting reflected and it is detected using a photodetector, and you have this surface plasmons, that is general surface plasma waves generated on appropriate conditions. You vary the angle so that the momentum conservation happens, and then you have at certain conditions this plasma waves generated at the dielectric metal interface. So at that particular condition, you will see that the photodetector shows a minimum signal. In all other angles, you have a considerable amount of reflection happening, but when the SPR is generated, these plasma waves are surface plasmon, the collective oscillation of electrons generated here. You have a dip in the signal. So that is actually represented like a dip in this reflectivity versus the position curve. Okay, you can change the angle and then monitor this. And as I mentioned earlier, if you have a gold coating over a dielectric, it is very much possible to attach antibodies to the gold, and these antibodies are ready to accept or bind antigens. So in that way, you will find that when the dielectric medium is changing here, you will find the condition for this SPR is changing and it occurs at a different angle. So you will find a change in the position of the angle. You may be familiar with these experiments. I am just introducing it as a sensor. There are a lot more things you have to consider. What is the width of this dip? What is the intensity of this dip? And where it is occurring? So many other algorithms are also involved in the actual calculation, but this is the basic idea of SPR. And coming to the fiber optic sensors, you have basically different configurations possible. You may be familiar with the Mach-Zehnder interferometer that you do in the lab. So if you set up such a Mach-Zehnder interferometer on a table or an optical bench, you will have these two mirrors, two beam splitters. This is a mirror, this is another mirror. These are two beam splitters. The light is splitted into two, and after reflection, they are again passing through this second beam splitter, and you can have the imaging from here or here, depending on your convenience, and the interference pattern can be formed. So in a similar way, this bulky setup can be replaced by a very compact setup if you make use of optical fibers. So you have a coupler here, optical fiber coupler, and you have another coupler here, and you have two arms. This one arm is termed as the reference arm, and the another arm is called the sensing arm, and you have the two detectors here. So in the sensing arm, it is exposed to the external parameters, physical, chemical, or whatever, strains, stress, force, etc. So, but this part is completely isolated, and depending on the phase difference generated between these two arms, you will have differences in these detectors, and from that you will be able to measure the parameter. And another one is a Sagnac interferometer. If you set up on a table, it will be a very bulky, and you have multiple mirrors, you have a beam splitter and 3 mirrors, and the light is actually transmitted and reflected from here. So the light is rotating in this, traveling in the clockwise as well as anti-clockwise direction. But if you imagine the entire setup is rotating in a particular direction, you will see that the time taken by the clockwise and the anti-clockwise propagating beams, pulses to reach the detector will be different. So that difference, from that difference, you can calculate what is the phase difference that is actually generated, from which you will be able to calculate the rotation. But this entire setup is bulky, and you can very well replace this setup using a optical fiber. So you have optical fiber or multiple number of coils, turns, multiple number of turns, and then they can be connected using a coupler, something like this. Okay, you have a detector, you have a source and a coupler. So the light moving in the clockwise and then the anti-clockwise direction, they can come to the detector and they can generate the phase difference if the entire setup is moving in a particular direction. So this is the explanation of the Sagnac effect, or this kind of rotation sensor. So this is the fiber coil, n number of turns, and it is connected to the output source through a 3 dB coupler, fiber coupler. So this setup can be it will take very small amount of space, so that it is applied in space applications, etc. And you can see here that the time taken for the clockwise propagating and the anti-clockwise propagating rays are different, the pulses are different, and from that the phase difference can. And in normal practice, if you calculate this phase difference, for example, shown here, you have a such a device. Suppose you are fixing it to the hour hand of a clock. We know it is moving very slowly. So if you calculate the delta phi that is generated, that is the phase difference that is generated by the clockwise and the anti-clockwise propagating see that it is very small. That is in this particular example, that is 7.2 into 10 raised to minus 7 radians only. But what happens here is that you have a term which is called the n. So you can have the n number of turns. You can increase the number of turns. So if you have 10,000 turns of the fiber that is used in the device, it can dramatically increase the delta phi. Significant. So if it is 1, it is this value, and if it is 10,000 turns, it can be 7.2 milliradians, which is very much measurable. So another type is the fiber Bragg grating sensors. So you have a optical fiber, and the core of the fiber is written with UV radiation. That means you have a permanent variation of refractive index periodically in the fiber core. So that will be leading to a forward and backward propagating modes coupling together, and you have a filter, that is optical filter, that is generated from this kind of gratings. That means you have a that is propagating in the forward direction, and depending on the periodicity of this refractive index variation that is written here, you will expect a particular wavelength, Bragg wavelength, to get reflected, and the other portions, all the other portions, if you are using a white light broad spectrum, all other region is transmitted. So I think you might have studied this earlier. So this also forms. So here what happens is a forward propagating and a backward propagating. So forward propagating beam actually generates the backward propagating. So here the difference is that you have one beta, that is the propagation constant of the forward propagation and the backward propagation. So the difference between them has to be capital K, which is equal to 2 pi by capital lambda. Here this capital lambda is nothing but the periodicity of the written grating. Important thing to be noticed here is that if you want to write a fiber Bragg grating for our communication wavelengths, for example, it is going to be, the periodicity requirement is going to be hundreds of nanometers, for example 500 to 600 nanometers. So it is not very easy to have fiber Bragg gratings. So another example is a distributed sensing using fiber Bragg grating. So you have a grating written onto the fiber with a grating period corresponding to lambda 1. You have in the same fiber you can write another grating with a periodicity corresponding to lambda 2. So n number of gratings is possible in the same fiber. So they can be inside the concrete structures or railway tracks, etc. So you can monitor different locations simultaneously using the same fiber at your control room. So that is the distributed sensing using FPG. So in the same fiber, you have different gratings written at different locations. So as I mentioned, the periodicity requirement is very stringent in fiber Bragg gratings, and that can be reduced by long period fiber gratings. So the long period gratings, here the coupling is occurring between forward propagating mode in the core and the modes that are propagating into the cladding. It is not a backward propagating, it is not to the backward propagating mode, the light coupling, the mode coupling is happening, but it is to the modes that are propagating into the cladding. So the requirement, if you calculate, is that the periodicity requirement in this case is not that stringent. even if you have periodicity of hundreds of micrometer, it can act as a grating, but the coupling is happening between the core mode to the cladding mode, both propagating in the forward direction only. Okay. Another type of sensor that we will discuss in detail today is the whispering gallery mode microcavity sensors. So these are nothing but some circular or spherical dielectric structures which provide resonant circulation of light. So once the light is trapped inside such a circular or spherical dielectric media, you can have frequency selections possible, like you can apply external parameters to this kind of cavities. So basically they are mirrorless cavities. They doesn't need any external mirror to generate any laser if you have a gain medium inside this. So there are different types of coupling mechanism possible, just like a prism coupling, and a polished fiber is used to couple light into the cavity, and a tapered fiber can be also used to couple light into the cavity. So it finds various applications, including in biology, communication, etc. So this is one example wherein you have a sphere, microsphere, the sphere with micron size, and a laser is coupled to this microsphere using a tapered fiber. So this is a tapered fiber, and we know in the tapered region you have maximum evanescent wave that is coming out to the energy coming out of the fiber, and it is easy to couple into the spherical cavity. So if it is a broad light source, you will find that a particular wavelength corresponding to this resonance will be missing in the output spectrum, and you can have all kind of biological binding kind of experiments done, like that we have mentioned earlier, antigen antibody interactions, etc., that will change the wavelength that is coupled into the sphere. So it can be used as a very good biosensors. So for example, this is one example that I am discussing about the microcavities used in biology. Okay, so you are familiar with the organic dyes used in photonics, the fluorescent materials. So in most of the biological experiments, they stain it. They use a large number of organic dyes. Okay, which are biocompatible. For example, green fluorescent protein, etc., yellow fluorescent protein, etc. So there are a large number of these fluorescent materials that can be used to stain the biological material, because normally they don't have any color, and the contrast will be very less between different subcellular subbiological structures. So they will be always having the same kind of transparency. So if you apply some kind of fluorescent material and then use the fluorescence microscopy, that is a common procedure in biology. Okay, so you can have a large number of fluorescent materials used for this purpose, and they have broad emission range, 30 to 100 nanometer. So the thing is that you are limited with the number of organic dyes that can be used simultaneously. So there is a limitation because they are having broad emission peaks. So that means there is a possibility that the signals from different locations or different structures, they can interfere. So it is fundamentally challenging to engineer molecules, these organic molecules, with much narrower spontaneous emission. So the normal fluorescence is very broad, so you cannot use a large number of colors. That is a limitation. So the optical resonance and stimulated emission allows spectral narrowing via coherent loss or gain. So one solution to this problem is make use of stimulated emission and optical resonance, something similar to the microspheres that we have discussed earlier. So where you have the resonance occurs, and it is very well possible to make lasers out of that structures. So they are very narrow emission structures. So this is just a comparison between the fluorescence and the stimulated emission. The spontaneous emission that we talk about, that is happening from a fluorescing material, it is emission that is happening in all the directions. It is not directional. And the emission is linear with the pump energy. Its spectrum is very broad. But if you compare this with a stimulated emission, you can see that the light that is generated is directional, and it is stimulated emission, and non-linear behavior. It is having a non-linear behavior. It is no more linear, because beyond certain pump intensity, you will have a huge increment in the intensity. And if you consider the spectrum, it is very, very narrow. So if you consider all these positive aspects of stimulated emission and implement them in the sensing applications, so a laser is going to be very far more useful compared to a sample which actually giving you spontaneous emission. So I will just go through some of the basic parameters of a sensor. I won't go to the details. I will just list them, then I will go to the topic. The sensitivity, the value of the response per analyte concentration. For example, for this kind of experiment, you have a prism and light is coupled to the SPR. For example, you have a gold layer coated here, very thin gold layer, onto which the antibodies are attached, and the antigens can be binded into the antibodies. So that will change the dielectric medium, and it can shift the SPR resonance peak. So this is for example, for this experiment, this is very general statement, and this is specific to this particular experiment. So the value of response per analyte concentration, that is sensitivity. Then detection accuracy, that means how accurate the measurement is. Limit of detection, what is the minimum concentration, that is the amount of analyte which can be sensed. Sensitivity, the chemicals, selectivity or specificity. Chemicals interference must be minimized, so there can be interference from other signals, other parameters, that has to be minimized for getting the correct results. Response time, time necessary for having about 95% of the response. Resolution, capability of the sensor to monitor the smallest difference in the analyte parameter. The resolution is not the characteristic of the sensor head, but that of the detector. So it will depend on the kind of detector that you use for the experiment. Repeatability, how many times a sensor can give the same result under similar conditions of operation. Reproducibility, the number of sensors manufactured with the same principle have the similar response. So you can manufacture a similar sensor again and again, and they will have all the same response. Noise, random variation of output signal which has no information. Dynamic range, the range between limit of detection and the maximum concentration which can be measured. This is a dynamic range. Linearity, a good sensor is expected to have linear calibration curve. It is linear when the output signal is directly proportional to the analyte concentration throughout the range of the sensor. Throughout the entire dynamic range, it is desirable to have a linear response. Drift, small undesirable change in the characteristic curve with time. Reusability, can the sensor be used again? If you construct fabricate a sensor, and can it be used again and again. That is called reusability. And if you are purchasing a sensor from the market, so it will be definitely having certain number of times that can be used. So in the economic perspective, it is very important. If you fabricate a sensor, you should be able to use it maximum number of time. So the commercial ones, they may not allow you to do this, and they want you to purchase it again and again. Shelf life. What happens to the performance when kept for a long time? So we are not using the sensor for a long time and then again trying to use it. Figure of merit. Ratio of the sensitivity of the sensor and the width of the spectral curve for this particular example that is provided here. So coming to the optical microcavities. As I mentioned earlier, it is a tool to trap the light. So it is always very interesting to store energy in the same form. For example, consider you are trying to trap the light and save it for future use. So it is very difficult task that we know because of many factors like the scattering, absorption, and all kind of losses that is available. But can you imagine a cavity which can contain light for considerable amount of time? So that is actually measured in terms of Q factor. So if you are able to confine light for some time efficiently, so that is an efficient optical microcavity. So it is a trap for the light. It uses resonant recirculation, and it can be used for lasers, filters, sensors, and switches. So obviously an ideal optical cavity should confine light forever, but in practice it is not, that we know. So how efficient the system is, or how much loss the system is offering, or how efficiently the light is resonating inside, is given by a factor called Q factor. So the examples shown here gives you the Q factor comparison for various biological and man-made systems, and it is very important to see that the optical microcavities shown here, these are the optical microcavities. They are offering the highest values for the Q factor. Okay, so they offer very good resonant recirculation, effective, efficient recirculation of light within them. And this is the most basic type of microcavity, which is called Fabry-Perot microcavity. Why it is microcavity? They have the size in microns, maybe tens of microns or hundreds of microns. So this is the most simplest one, the Fabry-Perot cavity, two plane mirrors separated by a distance, and in between the light actually bounces back, and we will see the details again. And this is a WGM kind of microcavity, which is called whispering gallery mode microcavity. We will see what it is later. And this one is distributed feedback microcavity. This is a corrugated structure, as you can see in the cavity, and this gives a distributed feedback when the light is circulating. And this is a photonic crystal cavity. You have periodic variation of refractive index. So dielectric constant is periodically varied, and you can have some kind of defects in it, and which can act as a cavity. So coming to the Fabry-Perot cavity, even though it is very simple, it is a two mirror cavity, two parallel mirrors, and the light is reflecting back and forth, and the optical resonance creates some or it can select certain frequencies only by resonance. So these are, for example, some of the lambdas that are selected, some of the frequencies that are transmitted through such a device, Fabry-Perot et al. So the requirement here is, even though the structure is very simple, it makes use of two mirrors. The requirement is that for reflectivity of and the quality of the mirrors have to be ensured, and the cavity has to be very, very short as possible, so that you will get very good quality modes that are selected. So for better light confinement, the reflectivity and the spacing between or the size of the cavity is very, very important. So this is actually gives the Q factor of such a cavity. So these are the selected frequencies by the Fabry-Perot type of cavity, and you can see that it depends very much on the reflectivity of the mirror. So if your reflectivity is higher, you have fine selection of frequency. Otherwise, the selected frequencies are broad. Okay, so this is how you can calculate the Q factor. Q factor is given by this value of the frequency divided by its width. So if the width is increasing, the Q factor will come down drastically. So coming to whispering gallery kind of structures as microcavities. So what is shown here is a church in London which is called St. Paul's Cathedral, where you have a dome gallery which is having 32-meter in diameter. Under this dome you have a dome here, and just below the dome you have a gallery. So inside the dome, this gallery is shown here in this figure. So what is shown here is when the people can sit here, they can walk, and they can whisper sound, and it can be very clearly heard on the other side. Okay, so clinging to the walls, the sound should decay the intensity only as the inverse of the distance rather than inverse square. So what we expect is a inverse square dependence of the sound signal, but it is actually resonating inside the wall, and it is very clearly audible on the other side. So at the 32-meter diameter circular gallery under the dome, even a single whisper from one side is clearly audible at the opposite end. And this is actually the acoustic resonance that is happening in St. Paul's Cathedral, and it was explained in 1878 by Lord Rayleigh in terms of the resonant recirculation of sound signal as the acoustic resonance. But later, exactly about 30 years later, a similar phenomena was observed in spherical structures for the light as well. So the scattering of spectra of plane waves from small particles were analyzed by Gustav Mie in 1908. So the geometric optics representation of light propagation in such a microsphere. So this is for the light and this is for the sound. So if you simulate the mode distribution of light within such cavity, it will look like this. So this is the mode distribution, and this is the actual representation, geometric optics representation of light propagation in such a microsphere resonator. So what is happening here is you have the light is continuously reflecting, and it actually resonantly recirculating. I mean, the constructive interference happens, and as in the case of a Fabry-Perot interference, the total path difference have to be integer multiple of lambda, so that constructive interference takes place. Here, for the efficient resonance, you see that the total path difference have to be integer multiple of lambda. They will be constructively interfered again and again, and those frequencies will be coming out enhanced. So here you have the the circumference of this sphere will determine the path, and you will have only selected number of frequencies coming out of, or selected, filtered out by this kind of structure. So why WGM micro resonator? Because even though the Fabry-Perot resonators are very easy to fabricate, or the structure looks very simple, it is not very easy to handle. They requires mirrors. For example, 2 miniature mirrors. It can be curved mirror, it can be plain mirrors, but the Q factor of such Fabry-Perot cavities are limited by the imperfections of the dielectric coatings on the mirrors. So the mirrors are very important and in Fabry-Perot cavity, and the quality of the mirrors are completely determined by the dielectric coating on the substrate. So it has to be highly polished and the alignment has to be very critical. So the scaling to large scale experiment, it's not commercially viable as well. So you can see different cavities here: Fabry-Perot type, whispering gallery type, and photonic crystal type. Okay, and you can see here, this is a disc, dielectric disc kind of thing, and you have a circular cavity, and you have 2 fibers, optical fibers here, something like that, and you can see the Q factors here, and here you have a sphere and you have a toroid kind of thing, both of which are supplied or the light is to this sphere as well as this toroid using a tapered optical fiber or a optical waveguide which is passing very close to it. So, but the beauty of the whispering gallery kind of resonators is that even though you can imagine very complicated cavity structures like disc, toroid, and this structure, etc., you can see that the Q factor for a sphere is considerably larger. Okay, it is very easy to fabricate as well. We will come to this later because this is a sphere of dielectric which can be very easily fabricated. Just have a comparison between the Fabry-Perot and WGM cavity. The Fabry-Perot cavity needs to decrease the cavity size for strong light confinement and the frequency selection. It needs to increase the reflectivity of the mirrors for reducing the optical losses. Q is limited by coating quality. But in WGM cavity, low optical losses. It has high Q. Miniature sizes is very much possible. You can create micron sized or polymer beads very easily. Spectral widths are very narrow. Resonant condition is 2 pi r is equal to m lambda. So the circumference of the sphere will determine the resonant wavelength. Q is limited by the surface quality and absorption only. It doesn't have any mirrors. So without the mirrors, the resonance is happening. High reflectivity over broad wavelength range. Coupling is by evanescent field analogous to quantum tunneling. So you can couple light into this sphere using an external fiber which is tapered. So by tapering the fiber, you are allowing more evanescent field to tunnel, leak outside the fiber, and it can couple very easily into the cavity. So without the mirrors, they are offering huge amount of Q value. So that is the beauty of WGM cavity. So a micro resonator, such a micro resonator can give you a huge number of properties or applications. For example, it can act as a switch, something like creation, transition, and termination of connections. It is possible using such a micro resonator. And a resonator itself, it can reinforce a frequency of a waveform like sound or light that we have already seen. It can reinforce a particular frequency and it can have output coupling. So if you consider what are these three functions, the switch, the resonator and optical coupling. So all these can be performed very well if you make use of a micro resonator based on whispering gallery mode. So we have defined what is switch, what is a resonator and what is optical coupling. So optical coupling is nothing but the light that is leaking from one waveguide to the another one. For example, in a dielectric, in a directional coupler, you have an optical fiber which is, for example, uncladded, and another optical fiber again uncladded, and these uncladded regions are sitting very close to each other for a certain distance L, so that you have input to only the first fiber and no input to the second fiber, and depending on the conditions, coupling conditions between the fiber 1 and fiber 2, you can have outputs coming from fiber 2 and the fiber 1, and the ratio of these powers of outputs will be determined by the coupling conditions, the length of the coupling region, etc. So you can have 50-50 coupling, 90-10 coupling, whatever type of coupling is possible. So it is basically optical tunneling from one fiber to the other fiber. So the function of a switch, the function of a resonator, the function of a optical coupling, all of these can be very easily implemented in a micro resonator. So optical ring resonator can redirect light, and specific frequencies are redirected. That means it can filter them, and also the size changes with thermal expansion. The size changes with thermal expansion. For example, you can have light coming through this particular fiber, and this can be a resonator, a spherical resonator or a circular resonator, and some part of light can be coupled into this spherical resonator. Okay, in that way you can couple out some kind of frequency out of your signal, and it can be dumped here, and the size and the coupling conditions can be managed or changed using thermal expansion. Okay, so in that way, in optical communication, you can add certain lambdas, and you can drop certain channels lambdas in optical communication. So usually what we do in optical communication is making use of an add drop multiplexer for this function. For example, you have multiple channels coming here, and you have a fiber Bragg grating sitting here, and the only wavelength, that is the Bragg wavelength, will be reflected from here, so that is dropped here, and you have another wavelength that is to be added from here, and this is added here to the channel and to the fiber system using a circulator, a device called circulator. The circulator is a 3-port device. So once the signal enters through any one of the port, it will go out through the next port. So it is a unidirectional device, the circulator. So once the fiber Bragg grating reflect one wavelength, it will enter the circulator and will through the first port of the circulator, and it will be dropped here. And similarly, another wavelength can be added from here through the circulator. It goes here, and it is FBG that is getting reflected, and it is added. But this function can be done using a micro resonator based on whispering gallery modes. And this kind of sensing we have already discussed, so they are having wide range of applications. And WGM resonators, they are simply monolithic circular dielectrics. They rely on total internal reflection rather than reflections from dielectric. So in other words, they doesn't require any mirrors. The quality of the surface will determine the Q factor. The Q is determined by the surface quality and absorption, and it is not limited by the mirror coating quality. High reflectivity over broad range of wavelengths, coupling to and from A resonant mode is achieved via external evanescent field at the points of total internal reflection. So analogous to quantum tunneling, the coupling is through evanescent field coupling, tunable strength and high reflectivity. So you can tune the strength and reflectivity. You can tune, for example, you can apply temperature, you can apply pressure, so that you can change the value of the circumference. So that will determine the coupled frequency. So, for example, a best example for such an experiment is shown here. It is a liquid droplet, so which act as a sensors in bio samples. Liquid droplet WGM lasers. So you have a droplet generator which generates liquid droplets, and it is trapped here using a laser. This is a pump laser coming from the bottom, and it suspends this spherical drop, and it can be excited using a laser, and its spectrum can be analyzed. So what are the frequencies that are trapped inside such a sphere? That can be monitored in a spectrometer. So this is a experiment, and you can see it can still generate a quality factor of the order of 10 raised to 8 to 10 raised to 9, and such experiments have been done. Carbon disulfide and liquid hydrogen droplets are used for this purpose, and if the liquid is containing some gain medium, that can be also used as a laser. What is generated coming out is a laser. Schematic diagram of the experimental setup of levitated micro drop. And inside what is shown is the trapped micro drop containing CDSC ZNS nanocrystal quantum dot. So this droplet contains CDSC ZNS nanocrystals. So they emit light, and they can act as a WGM laser. And these kind of things are also applied in biology. For example, from this paper it is taken, you can see certain cells, they naturally contain these spherical droplets, which are nothing but the lipids. So certain cells contains naturally this kind of spherical droplets, and if you treat them with some kind of fluorescent material, organic dyes, they can absorb organic dye, and when you excite light from outside, excite these cells from an external laser source, the light can be trapped inside, and they can generate specific frequencies, something like laser. So they are called biological lasers. So a cell, a liquid drop inside the cell act as a microcavity and giving out laser radiation. You can see they are very, very fine with high Q value frequencies that are recorded in a spectrometer. Or you can, instead of the naturally occurring liquid drop inside the cell, you can introduce certain dielectric beads like glass beads or polymer beads. The polymer can be fluorescing polymer, and they can very well go inside the cell, and you can externally pump them, and they can generate such laser modes. They can be analyzed externally using a spectrometer. So it can be used for sensing and other applications in biological media. And another one is tagging and sensing applications of solid intracellular microcavities. As mentioned earlier, you have solid microspheres which are doped with fluorescing material, and once they get into the cell and once they are excited from external source, they can generate this kind of WGM modes, whispering gallery modes inside. And what is shown in this figure is they makes use of a confocal hyperspectral imaging. They externally pump using an external source of LED source of 455 nanometer LED is used to excite this biological cell, which is doped with which have already internalized this kind of microcavities. That is, it can be polymer beads, it can be glass beads. So they emit light in this fashion. This is a confocal image. And once you get the confocal image, it is also the hyperspectral details are also taken using the hyperspectral imaging, so that the frequency content of this circle intensity pattern can be analyzed. So depending on the color that is analyzed, you can simply calculate the size of the bead, because the WGM frequencies will be perfectly matched with the circumference of the bead. So in that way, it can be used for tagging and sensing applications. When you have multiple cells, each of the cells are internalized with different sized and different fluorescent material doped into them. So that means a large number of cells can be simultaneously tagged and sensed. So usually the WGM resonators are made of silica. The majority of solid WGM resonators are made up of silica in a spherical shape, mostly by melting fiber tapers. Due to the surface tension, melted part of the silica fiber tapers forms into microsphere. So you imagine an optical fiber, and the end of the optical fiber is melted, and usually it forms a spherical shape. And this sphere can very well act as a WGM cavity. Okay, and if you dop this one with some gain medium, it can also act as a WGM laser. So these are various examples of microspheres, microfiber, microtoroid, capillary, then microdisc, split disc, microbottle, and ring resonators. So you can create a large number of polymer WGM resonator. If you come to polymer, so we have said it is a glass that we have discussed, and now you can see that if you make use of polymer, it is very easily you can, because the temperature requirement is very small in polymer. That is, it requires only 200 degree for your processing, unlike a 2000 degree for the glass. So a large number of micro goblet lasers fabricated by parallel solution processing method, a large number of such microstructures based on PMMA polymer is shown here. You can compare the properties of silica. You have a large thermal expansion coefficient, 2 orders greater, and thermo-optic coefficient also 2 orders greater compared to the silica. So it is very easy for handling polymers compared to silica. And this is a example shown. You have a circular cavity of another circular cavity, and they are joined together, and once they are coupled together, it is very easy to select the modes. So once the coupling happens, the resonance condition changes, it becomes more stringent, and you can see the resonant condition should satisfy the size of this cavity and the size of this cavity, so that it is very easy to modulate or select the frequency that is coming out. So for single mode operation, you have two fibers close to each other. This is the cross section, and this is the actual photograph. One fiber, doped fiber, another doped fiber with a different diameter, sitting very close to each other, and we can externally excite them, and the frequency selected is a single mode operation that is shown here. And the polymers have a lot of applications, like they have very low processing temperature. Even though if you make optical fiber out of polymers like PMMA, they offer large amount of loss, but the processing temperature is very small and very easy to fabricate and easy to handle. And one thing to be noticed here is they offer minimum loss, minimum attenuation in the visible region. So in the commercial optical fibers, you expect minimum losses in the infrared region, but if you make optical fibers from polymers, you see that it is going to offer minimum loss in the visible region. So that is one important property. And again, at the same time, it can offer all the other benefits of optical fibers, common optical fibers, and by making use of these two advantages, we started fabrication of polymer optical fibers, and we doped them with different fluorescing materials. So for example, it can be combination of materials that is doped into polymer, and if you excite them with a particular color, appropriate color laser, you can expect multiple colors, and there is a possibility of multi-wavelength amplification and lacing from this kind of optical fibers. So we can manufacture them in a optical fiber drawing station. So we fabricated also the graded index optical fibers. Graded index fiber is very important in the management of dispersion. If you have studied the optical fibers, you can have basically three types. One is multi-mode step index, multi-mode step index, single mode step index, and the graded index structure. So if you have a larger diameter fiber, it is always desirable to have a graded index refractive index profile in the core. So how to create a graded index structure? So it is very easy to conceive an N1 and N2, like N1 in the core and N2 in the cladding. But what happens if you require a maximum refractive index along the axis, and it has to gradually come down to the cladding refractive index gradually? So such an experiment can be done with using the process called interfacial gel polymerization. Here, what we can see here is a tube, cross section of a tube, and this is a polymer already, and inside you have another polymerization to be happening. So that means you have the monomer which is to be polymerized again, that is A, and another chemical which is B, which is larger molecule, and they are mixed and they are heated, and the heating is actually initiated from the sides. This is a tube cross section. Okay, something like this. So the heat is actually applied from the sides, and the polymerization begins from the walls, and it solidifies, and finally the portion is solidified at the axis. So because of the larger size of the B compared to A, only A are diffusing into the gel phase that is happening initially here, and this is still liquid, and the bigger molecules like B, they are pushed towards the axis, and only in the final phase of polymerization the B is polymerized. So in that process, maximum number of B molecules are pushed towards the axis, and they will be polymerized in the final phase of polymerization. So you will have a large value of refractive index at the axis compared to the interface. So in that way, you will be able to generate a graded index structure. And this is a famous cartoon showing the effect of signals while propagating through a fiber. So to tall people actually crossing the tunnel, tall and lean people crossing the tunnel, and they come out as short and fat. They become short because of the attenuation, and they become fat because of the dispersion. And a graded index fiber is one choice to decrease the dispersion, so that every mode that is traveling through the fiber will in time. So that is a logic behind such a graded index structure. This is a graded index kind of polymer that is generated, and once such a graded index polymer is fabricated, it is desirable to study its refractive index pattern, refractive index profile. For that, we usually take a small cross section of the rod. It is kept in one of the arms of a Mach-Zehnder interferometer, and the interference pattern is imaged using a high quality camera, and you will find interference fringes something like this, and from which you will be able to calculate what is the graded index structure that is formed actually in the sample. And that is one, this is one interesting result that we obtained. We not only add the high refractive index material, but also some gain material like gain medium like rhodamin B, rhodamin 6G, etc., which are fluorescent dyes. So this is a comparison between step index and graded index, step index and graded index with another fluorescent dye, and this is step index and graded index with a combination of these two dyes. And what we can see here is significant narrowing of emission when compared to the step index in the graded index. So graded index structures are confining light more efficiently, and they can give you amplified spontaneous emission easily compared with the step index, and also they generate lasing frequencies beyond a certain pump power. So no lasing was observed in any of the step index structures, but lasing was observed in the graded index structure. So then later there was a considerable interest in the photonic crystal fibers. So many people were fabricating such structures, and this is a solid core structure and this is a hollow core structure, and we also tried to generate that structure. These are silica structures that are reported, but here we tried from the plastic we tried to do the same thing, but it was not a success. How it was done, it was something like this. We initially fabricated hollow polymer optical fibers, and then we stacked different hollow structures into this, and then again we drawn such a fiber. But you can see many of the holes were collapsed, and many of them were, were not formed in the actual desired manner. But what we find from here is that we started working on these hollow individual optical fibers, and we found that they can act as very good microcavities which can confine light, and that was very easy to fabricate as well. So we started working on this by doping different materials like nanoparticles, dyes, fluorescent dyes, etc. And this is a cross section of such an optical fiber which is doped with rhodamin. You can find here the WGM, whispering gallery kind of circulation of light is possible here, and the emitted frequencies can be very well matched with the circumference that is calculated. And one important thing to be noticed here is that if you reduce the thickness of the tube, so this is the cross section of the fiber. Okay, this is not a ring. It has a length, and this is the cross section. And if you imagine that the plastic, the polymer thickness, layer of the thickness is much smaller, it actually leads to a different kinds of resonance. It's a normal total internal reflection. It goes to the inner interface, it goes to the outer interface. So this is a normal TAR, but here this is not going into the inner interface. It is simply circulating in the outer interface, and this is exactly the whispering gallery mode, and the observed frequencies were perfectly matched with the observed ones, the calculated ones. And there are different works that are going on. For example, here is a capillary, and this is a glass capillary. Glass is doped with erbium, ytterbium, rare earth material, and it is excited with a 980 nanometer laser, and some fluid, it can be gas or liquid, it is flowing through the capillary, and the excitation of WGM actually locally heats this capillary, and depending on the heat, the movement of the fluid is controlled, and the fluid flow can be completely monitored by monitoring the light that is propagating through this fiber. So This is a fiber which makes use to excite the WGM in the capillary. So it can be an evanescent wave coupling from here. So what is transmitted is, in the transmitted spectrum, you will have a dip because corresponding to this WGM, one wavelength is actually dropped. And this is very much useful for acting as a flow sensor, something like anemometer. So the local heating by the WGM controls the liquid flow. So it can be a flow sensor. So coupling techniques are different. It can be an active WGM coupling or passive WGM coupling. Active means your fiber or your waveguide contains some active medium like fluorescent dye. So you excite with a laser, and since this has a fluorescent dye, it emits some radiation, and the emitted radiation is actually the whispering gallery modes, corresponding to the whispering gallery modes, and these frequencies are very well matched with the circumference. Okay, so this is called the active WGM resonator. It can be passive as well. In the passive kind of thing, the optical fiber, which is the polymer optical fiber, it doesn't contain any active medium. It cannot generate its own light, but the tapered fiber actually couples light into that. But what is monitored here is the light that is transmitted through the original optical fiber. So you will find dips in the transmission spectrum. These dips are corresponding to the frequencies that are coupled into the normal optical fiber. So this optical fiber, polymer optical fiber, to which the light is coupled, is not generating its own light, but it actually traps some of the frequencies of light which is actually coupled into it. So this is one electric field distribution using the COMSOL simulation. You can see this can be a capillary, cross section of the capillary, and this is the light that is passing through a optical fiber, and the light being coupled into the capillary. So a temperature sensor was demonstrated based on this principle. For example, this is a active temperature sensor because the material inside, that is kept inside this chamber, is heated, and that is actually the cavity. But the WGM cavity here is an optical fiber, plastic polymer optical fiber doped with dye, and it can generate its own light, and what is generated is the laser, and that laser is changing its wavelength because it is locally heated using a temperature. So it is an active kind of temperature sensor. And this is a passive sensor wherein the tapered fiber simply couples some light into the optical fiber. So the light the original fiber is given to a spectrometer or optical spectrum analyzer, and that dip is actually monitored. So in a passive sensor, usually this dip is monitored. In an active sensor, the emission of light from the actual fiber, that is the WGM cavity itself, is monitored. That is a difference. So go to the next. So micro ring.
Sir.
Yes.
We have less time. Please conclude.
Okay. How much time I have? Another 10 minutes?
Already we have 10 minutes extra. You can conclude as per your convenience.
Okay, 10 minutes I will, in 10 minutes I will conclude. Okay.
Second session will start, that resource person already joined. Huh?
Okay.
Sir. Okay. Please.
Okay. So in the micro ring embedded hollow polymer fiber as a WGM laser, we have this optical fiber, hollow optical fiber, in which we have a very thin layer of light, thin layer of gain medium that is coated inside. So that actually leads to a very good modulation. We have the modulation is very huge, something like single mode operation is possible because the light is being coupled into the cladding region and also into this thin layer of gain medium. So the conditions becomes more stringent, and single mode operation is very well possible. You can see a single mode operation. And similarly, a micro ring embedded hollow optical fiber is used for refractive index sensing, because inside this capillary kind of thing, we can put liquids of different refractive indices, and this is going to change the emission wavelengths of the WGM laser. So in that way, it can act as a sensor, refractive index sensor. So here it's a strain sensor. In the strain sensor, you have a hollow optical fiber doped with fluorescent material. So it's an active kind of sensing, and it is the sensor, I mean the fiber is actually applied some strain and in this direction, so that it can change the diameter of the fiber, and accordingly you can just monitor the shift in the frequencies, and it can very well act as a strain sensor. Similarly, thermo-optic tuning is also done. The temperature of the cavity, which is actually a doped optical fiber, is changed, and it can either change its refractive index or it can change its diameter with temperature. So it can act as a sensor for temperature. It can also can be a size tuning. It can choose the size. I mean, the diameter of the fiber can be changed, or the temperature can be applied. So in both way, the emission wavelength can be tuned. So this is the hollow fiber under question, and its diameter can be changed or its temperature can be changed, so that the output wavelengths can be tuned. So we have also demonstrated some kind of all optical tuning without external heating. We can also give another laser for heating, which can also result in this kind of tuning. It's a temperature tuning. And this is a microsphere kept inside a cavity, which can be used as a ammonia gas concentration sensor. And this is given this is pumped using a tapered optical fiber. The tapered optical fiber can couple light into this microsphere. So with this, I will wind up. This is the final one, and this is a graded index structure that is being constructed by our group, and this is cladding, and this is the core. As I mentioned, this is a graded index region. So, and also it contains some fluorescent material. So once pumped from side, this fiber not only generates light laser, but WGM laser is actually getting focused because of the graded index structure. So in effect, the circumference of this circulation of this resonance is actually changing with distance, and the selected frequencies are different. If I monitor light from here, the selected frequencies are different. If I monitor light from here, so with different lengths, different frequencies are generated for the laser. So one important thing to be noticed here is, from all these lasers, the power that is generated from these microstructures are very, very small, and we just wanted to amplify them. And currently we are trying to amplify this hollow structure, the laser modes that are generated by this hollow structure, something like this, using an amplifier using a graded index fiber. So you have a hollow structure which is acting as an oscillator, and a graded index structure which is acting as an amplifier, and we are constructing them in a single piece of fiber, and that experiments are being done right now. And let me conclude. The doped polymer fiber optical fiber can be very good candidate for fabrication of optical microcavities. Polymer based microcavities can offer tunable low threshold lasing in visible region. Graded index hollow and micro ring embedded types of polymer micro lasers can be used for sensing a variety of physical parameters. Photostability of organic dye doped polymer lasers can be improved by the incorporation of metal nanoparticles. Micro ring embedded hollow microcavity offers strong modulation leading to single mode operation. improved directionality of WGM lasing can be realized by an asymmetric cavity. I would like to acknowledge my students and the funding agencies, and these two universities have helped us in achieving these aims, and also most of our students were able to do many of their experiments in these universities. Thank you once again, Abhijit Yadav and the Atal FDP program for giving me an opportunity to share some of the work that are conducted in our university. Thank you, all the participants.
Thank you, sir. Thank you, sir, for a wonderful lecture. Participants, now the session is open for discussion. If you have any queries, you can raise your hand or you can unmute yourself and ask the question to Honorable Sir. Sir, I have one question, means one not question.
Okay,
one thing, in fabrication of a graded index polymer optical fiber, we have atoms A absorbed and the B molecules pushed towards the axis of the core, for example.
Okay.
What is the force responsible there to push all the B molecules at the center?
So actually, initially, the heating is actually originating from the axis. I mean, from the periphery.
Yes.
So you can consider this as a tube, cross section of a tube. This is actually taken inside a test tube. Okay, test tube kind of thing. And you have initially a tube-like structure. This is a tube. This is solid.
Okay.
This is solid. This is solid made of the molecule A. For example, monomer. Okay. So initially you made a polymer tube, which is basically nothing but a solid form of this A. Okay. So then you start filling this tube with both A and B. Then you heat it. That means you apply heat from the sides. Okay.
Yes.
So what happens initially is this inner wall of the tube, which is filled with the liquid, it actually becomes a gel form.
Okay.
This becomes gel form, and this is still liquid.
Yes.
At the center, it is still liquid.
Yes.
Okay.
Sir.
So the gel form means A molecules are smaller in size. They can diffuse into this gel form more easily.
Yes.
It's a kind of diffusion. A is diffused into the gel form more easily, but B is being bigger. It is unable to diffuse into this. Okay. So, but at that same time, this is already solidified. So the next layer becomes a something like a gel form. Okay. So again, A is able to diffuse into the gel form. B is still not. But certain number of B is actually trapped here because of the solidification. But finally, you have large number of B at the center. That is the idea behind.
Yes, sir. I got it. No. Thank you, sir. Thank you, sir. Okay. Participants, if you have any questions, you can ask. If there are no more questions, I would like to thank Professor Kailash sir for delivering a very good talk on polymer fiber optic micro lasers for sensing applications. The talk covered a lot of things, starting from the sensor related activities to fluorescence microscopy and optical microcavities, and then the resonators, micro resonators. Then we have a fabrication of a graded index polymer optical fibers, refractive index profile measurement in fibers. All the things he has covered in his talk, and this talk is very informative, illustrative. Not only this, he has used animations in between his presentation that have created a lot of effects on the minds of our participants. So thank you, sir, for your wonderful lecture, wonderful, informative, and a nice presentation. Thank you, sir. On the behalf of my college, Rajarshi Shaumavdala Latur, on the behalf of myself and on the behalf of Atal Academy, New Delhi, I thank from my bottom of heart. Thank you, sir.
Thank you, one and all. Thank you.
Thank you, sir. Thank you, sir.